As we move into section 13.4 in Algebra 2, we're starting to get into the second half of chapter 13. So the beginning was all kind of like an introduction to trig, and now what we're going to start doing here for the next, 3 or 4 sections is to start doing one of the other big things we do in Algebra 2, graphing new styles of functions. And we're going to begin graphing trigonometric functions now by starting with sine. The way this book splits things up, 13.5 is going to be cosine, 13.6 is going to be tangent, and 13.7 kind of mixes all of those together and gives you a lot of variations on that. What that means is that this section is going to be pretty straightforward. I've got a lot of things within this file here, guys, but we're really just going to do 3 problems here today. And they're all going to be relatively basic and similar. So we're going to try to graph y equals the sine of x. So eventually, not yet, we're going to be drawing ourselves a graph and trying to figure out what this thing looks like. But, like in a lot of other chapters we've done this year, when we begin something totally new and we have no idea what the graph looks like, it's probably a good idea to fall back on something we've always done, and that is to make a table of values to help us figure out what this graph is going to look like. So very simply, I'm just going to make a long T-chart right here, guys, with an X column and a Y column. And we're going to start picking some X values and figuring out what Y is. Now, what I want you guys to realize is that when we're looking at the function right here, Y is equal to sine of X, X is the number that comes immediately after the sine. And as hopefully we established earlier on here, anytime you write sine or cosine or tangent, it's followed immediately by an angle. So the number we're putting in for x is the angle that we're going to take the sine or cosine or tangent of. So the first angle we're going to start with here is going to be 0. And by the way, I should probably list, and I know you guys are going to love this, we're going to do things completely in radians from here on out, guys. So x is our first angle measured in radians. And what we're going to do then in this chart is just try to figure out what the sine value is at all of these different angles. And to do that, if you have these numbers all memorized, good for you guys, but I kind of doubt that you do, I want to take a second here and draw myself a unit circle. Ooh, that got ugly there, but all right, good enough. And start talking about our sine value at each point on that unit circle. I didn't like that at all. I'm going to redraw that. Okay, slightly better. Okay, 0 radians, guys, is this point located right over here. And when we're talking about our sine value, it is always the y-coordinate at whatever ordered pair that we're at. So I'm hoping you guys remember this. On a unit circle with a radius of 1, this ordered pair we have here is 1, 0. And sine is always your y-coordinate. The y-coordinate right there is 0. So there we go, guys. The sine of 0 radians is 0. The next thing we're going to do is I'm going to have you guys skip, let's see, we're going to skip 1, 2, 3 lines, and then the next angle we're going to put in this table right here is going to be pi over 2, which brings us right up here. That's our next quadrantal angle, and that one is the ordered pair 0, 1. And at pi over 2, as always, our sine ratio, our value, is our y-coordinate at that point, which in this case is a 1. So the sine of pi over 2 is 1. We're going to move over here now, guys, to where x is going to be pi. And the sine, which is the y-coordinate at this point right here, well, that's a -1, 0. Your y-coordinate there is 0. Let's see, can I cram a little bit more in here without scrolling? The next angle we're going to go to is straight down now, south on the unit circle. That's 3 pi over 2, and this is the ordered pair of 0, -1. Once again, sine is our y-coordinate, which in this case is -1. And then we're going to go all the way back right over here to where we started, guys. That would be 2 pi. And remember that 2 pi and 0 right up here are coterminal angles. It's tempting to think they're the same angle, and they're really not, but they end in the same place. So the y-coordinate there is once again 0. And if you take a look at the 5 ordered pairs that we've now created in the table, you start to notice that your y values do something interesting. 0, 1, 0, -1, 0 again. They kind of seem to be bouncing back and forth between a couple of values. So I will come back and fill in those 3 missing lines in just a second, but I think now is probably a good time to start thinking about what our graph should actually look like. All right, so what we're going to try to do, guys, the graph that we very often make when we're graphing trigonometric functions is maybe a little bit different than what we did with a lot of other things here. So for these graphs, what we're going to do, and guys, you don't want to make this small in your notes if you're writing some stuff down. Try to make this take up most of the width, maybe not all, but most of the width of a page in your notes here. So I'm going to draw a very long x-axis, everybody, looking something like that. But my y-axis, which of course I'm going to draw in the middle here, doesn't need to be that big, and you'll see why here relatively soon. So here's my y-axis, and here's my x-axis. The next thing we're going to do is we're going to start labeling where we are on the x-axis. Now, if you take a look back at our table here that we did on slide number 1, the biggest x value we chose to put in this table here was 2 pi. I'm going to take advantage of that fact here, everybody. So what that means then is when I shoot all the way out to the right, about as far as I gave myself room to do, I'm going to call that 2 pi right there. Okay, now obviously the origin right here in the middle, guys, that is the point 0, 0. So what that means is that halfway between 0 and 2 pi, that's going to be 1 pi. We'll just write that as pi. Halfway between 0 and pi, which is right about here, is going to be pi over 2. Halfway between pi and 2 pi, right there, is going to be 3 pi over 2. And there's a reason I'm writing that up on top. You'll see why a little bit later. Now I want to try to do the same thing on the left-hand side. And ideally, my spacing would be about perfect. I doubt that it is, but okay, fine. This is going to be negative 2 pi. Halfway between 0 and negative 2 pi is negative pi. Right here, this is going to be a negative pi over 2. Again, you'll see why I wrote that on the top in a second. And then here is going to be negative 3 pi over 2. There certainly are more angles than this, everybody, but that's a good start. And hopefully I drew this fairly symmetrically. I don't think I did. It feels like this distance right here is a lot shorter than this distance right here, and those really should be the same. But hey, this is what happens when you draw things by hand. As long as they're labeled well, we'll get the gist of it. Now, the other thing I want to do is I want to label my y-axis. But I want to try to be accurate about this just so you guys get a sense of what's going on here. What I want to focus on is this value right here, which is pi. And that means, everybody, don't draw this in your notes, that the distance from here to here, is pi, which is roughly, not exactly, 3 units right there. It's actually 3.14. That means that this distance from here to here is half of pi, which is about 1.57. I'll just write it as 1.5. Now, if you go back to the table that we made here, everybody, the biggest value that we came up with for sign of x in this problem was 1. The smallest value it looks like we've come up with so far is negative 1. So that means that as I go to label this graph, the highest I need to go here is 1. And if I care about getting the scale accurate, if this distance right here in red is about 1.5, then 1 needs to be less than that distance right there, about 2/3 of it. So I'm just going to guess right here and say, okay, that right there is going to be roughly 1, and I'll try to go about the same distance down here on the bottom and say that distance is going to be negative 1. Now again, I'm going to get all this red stuff out of the way. It is not essential, guys, that that looks exactly the way that it's quote-unquote supposed to, but I'd kind of like that to be accurate for you guys as we get started. Now that we've got a pretty decent graph laid out right here, we're going to go ahead. I'm going to switch back to blue. We'll switch to purple. All right, and I'm going to plot the 5 points that we had in that table. The first one we wrote down was 0, 0, so that's a dot right there at the origin. Then we had pi over 2, 1, which puts us here into the first quadrant. Pi 0 was the third ordered pair. 3 pi over 2, negative 1 got us to right about here, and then we got back to 2 pi and 0. And that's where we are right now. And this is a rather unique arrangement of points on our graph. We haven't really seen anything like this year, where the function goes up and then down and then down and then up again. And the fun part about this is, if you were to keep going around the unit circle over and over and over again, you start to see that this pattern just repeats itself. We did one complete revolution to get here to 2 pi, but if I were going to keep going to, let's say this would be 5 pi over 2, I'm back to a sine value of 1. And then if we were going to keep going to 3 pi, that's a sine value of 0. This guy right here would be 3.5, 7 pi over 2. That would be a sine value of negative 1. And if I kept going then to 4 pi, we'd be right back to 0. This thing keeps repeating itself over and over and over again. And the same thing happens if we go backwards. Let me draw a much smaller unit circle right down here. What if I were to start thinking about negative angles? Like, for example, starting here, if we went backwards to negative pi over 2, sine would be your y-coordinate right there, which is negative 1. So at negative pi over 2, we have a sine value of negative 1. If I kept going here to negative pi, sine is my y value here, which is 0 again. All right, negative 3 pi over 2 gets me up here. Sine is my y value there, which is 1. And then back to negative 2 pi, that's right back where we started. We're back to 0. So boy, take a look. I think we've got 9 purple dots on this graph. We're starting to get the sense for what this thing looks like, everybody. Now, there's a wrong way to handle what happens next. The wrong way, don't do this in your notes, is just to draw this Charlie Brown zigzag thing that's just kind of a series of straight lines. Sine curves are actually far more smooth and more elegant than that right there. And I wanted to just illustrate that concept, by going back to these 3 blanks that we left here a while ago. The 3 angles that we skipped that are greater than 0 but less than pi over 2, the first one, and this should sound familiar to you guys from that unit circle diagram we've been using so far, is pi over 6. The next one then is pi over 4, and the third and final one there is pi over 3. Guys, these are the 3 angles that are located roughly here and here and here on the unit circle. So at pi over 6, we're talking about this point right here. And if I drew my triangle, it looks something like that with a 30-degree reference angle. Sine, once again, is your y-coordinate, everybody, the length of this piece right here. And hopefully you guys have this down from earlier in the chapter. That y value right there is 1/2. At pi over 4, oh, this starts to get messy now, guys. At pi over 4, we're now talking about this point right here. So that guy is supposed to be a 45, 45, 90 triangle. And this vertical piece right here has an irrational value of root 2 over 2. And pi over 3, I'll do this one in red, is this angle right up here, everybody. That's another 30, 60, 90. Sine is your y-coordinate right there, which is the square root of 3 over 2. And if it helps you with the graphing, everybody knows that 1/2 is 0.5. Root 2 over 2 is approximately 0.707, and root 3 over 2 is 0.866. Those are rounded, of course, those last two. Now, you can use that information to kind of fill in some gaps on this graph right here. All right, let's take a look. I'm going to switch back to black for just a second here. Let's see. Pi over 4 would be right there between 0 and pi over 2. Pi over 6 would be just a little bit to the left of that. Pi over 3 would be a little bit to the right of that. And this right here would be a y value of about 1/2. So what points did we come up with, guys? At pi over 6, we came up with a y value of 1/2. So we should get a point right about there. At pi over 4, it was root 2 over 2, which is 0.7, which is about there. Just kind of eyeballing here, guys, something like that. And at pi over 3, it went all the way up to 0.866. Now, what I'm really hoping you guys are going to see here is that this graph is not linear, but it has a little curve to it, everybody. It passes through the origin with a slope of like 45 degrees. Actually, it's exactly 45 degrees. That's using some calculus that you guys will hopefully learn about in a couple years. And the curve kind of bends downward, and it's actually, everybody, horizontal as it passes through that point right there at pi over 2, 1. And I want you to concentrate and really get the shape of that one little curve right there right, because we're now going to just copy that curvature all over the place. From pi over 2 to pi, this thing now comes down like this. And then it does more or less the same thing here, everybody, as it comes from pi over 2, from pi to 3 pi over 2, and then up to 2 pi. So it's definitely got some bend to it, everybody. It's not just a series of straight line segments here, but we want to try, especially as we're getting started, to get each one of those curves roughly accurate here. So 2 things to focus on. Every time your curve passes through the x-axis, like here and here and here, it should be doing so at about a 45-degree angle. Again, not about, exactly a 45-degree angle. And every time it passes through either a high point or a low point, it should actually be horizontal at those points right there. So those are just some ideas to keep in mind if you want this sine curve to look as smooth and as accurate as it possibly can. So I'm just going to draw the end of this. It's always harder for me going from right to left. And there you go, guys. And I'll draw some arrows at the end here indicating that this graph keeps on going forever and ever and ever. But that's what our graph, everybody, of y is equal to the sine of x looks like. Now, all year long, we want to label these things right here, guys. This is going to be your parent graph for what a sine function looks like. And before we put a bow on this thing, guys, let's just talk about a little bit of vocab right here that we should understand. First thing, something we've talked about all year long, the domain of this function. The set of all x values that you can put into a function and get a real result. So really, graphically, the question is, how wide does this function go? How far left and how far right? Well, this thing never ends, guys. It can keep going as long as we want it right here from left to right. So our domain here is all real numbers, which just means it extends infinitely far to the left and infinitely far to the right. Once you start talking about domain, we also need to talk about range. And this is the set of all y values. And this one is limited. What you guys will notice is that the lowest value on this curve that you're ever going to hit is -1, and the highest value you're ever going to hit is +1. So there's lots of ways of writing that, but what I like to do is this compound inequality. -1 is less than or equal to y. Now let me stop you right there. If I read that backwards from right to left, it would be y is greater than or equal to -1. But we write it this way because now we keep going, and y in turn is less than or equal to +1. So y is always sandwiched in between -1 and 1. Okay, here's a word that maybe you guys have learned from some science classes before, and that word is amplitude. Now, I guess I haven't used the W word yet, guys. The graph we've come up with here is a wave. So you'll hear this referred to as a sine wave before. And an amplitude is basically a measure of how tall a wave is. What you're going to do is find the easiest way to do this is to find a high point or a peak right here. And you're going to measure the distance back to what we call the midline of the graph, kind of the center of this whole thing. And that distance right there is your amplitude. And in this graph, that amplitude is just going to be 1, but that's something that's going to change a little bit from one problem to another. Another word we want to introduce right here that you guys may or may not know is the concept of a period. Something that repeats itself over and over and over again, we say is a periodic function. And that's what happens right here. So we started graphing this thing right here at the origin, 0, 0. And the question then is, how long did it take, or how far did we have to go for this thing to complete one full cycle? So what did this graph do, guys? It came up, and then it went back down, but then it now went below the axis and came back up, and this is where we ended that one cycle right there. So from here to here, everybody, is one complete period of this cycle right here. Notice it just, here's another period, and then there would be another one over here on the right at the end, and so on and so on. So our period here, guys, in this particular graph, it took 2 pi units for this thing to repeat itself. And that actually should be the same distance if you measure, let's say, from peak to peak right here. That should be a distance of 2 pi. Or if you measured from this low point, which we call a trough, to another low point, that should be the same period right there of 2 pi. So a couple of important things to talk about right there. Okay. All right. That's, I think, all we wanted to say about this first graph. And there we go. The word, I'm sorry, one more word that I wanted to use right here. The word oscillating. is a word that we often use to describe a sine wave here. It oscillates, kind of like you might have a fan on a stand at home that kind of blows and it goes back and forth, left, right, and does that over and over again. An oscillating function just goes back and forth between two set values. And in this one right here, that max value is 1, that minimum value is -1, and the function just keeps going back and forth between those values. Okay, we're going to move on and do 2 more examples here, guys, but these 2 are going to go much quicker than the ones that we just did. All right, so y is equal to 3 sine of x. So the only difference right here between this and the parent graph we just drew is the presence of that 3. And as we've talked about all year long, guys, any function that you have, when you multiply it by a number bigger than 1, like 3, that is what gives us a vertical stretch. This graph is going to be taller than the graph that we just came up with right here by a factor of 3. Now, if you want to, we could still make another table, and I'll make this go much quicker than the last one here, guys. When we put in a 0, sine of 0, remember, guys, that happens first. Sine of 0 is still 0, times 3 is still 0. That didn't change. Now at pi over 2, the sine of pi over 2, this is straight up on the unit circle now. The sine of pi over 2 is 1, but that gets multiplied by 3 for a 3 value right there. Okay, pi was our next quadrantal angle, so the sine of pi is 0 times 3 is still 0. Maybe you see the pattern now. 3 pi over 2, we're now straight down on the unit circle where sine is -1, and that times 3 is -3. And when we come back to 2 pi, sine of 2 pi, our y-coordinate is 0, times 3 is 0. So, a little bit of a variation right here between some of the y values that we came up with before and what we're coming up with now, but for the most part, guys, things are going to be relatively similar. Okay, so let's try to do the same thing, although with the 3, I might need to make this graph a little bit taller than I did with my previous graph. I'm still going to go out to 2 pi on my x-axis and work backwards from there. So here's going to be 1 pi, pi over 2, 3 pi over 2. And again, let's see if I did the same thing here, guys. I kind of think that I did. I tend to not draw this left side of the x-axis quite as far as I should here. So -2 pi, again, it doesn't matter that this is totally accurate, but close enough. Okay, -pi over 2, -3 pi over 2, good. Now, how tall do we need to make this graph? 3 looks like our maximum, -3 looks like our minimum. And remember, guys, this distance from the origin to pi is roughly 3. So that is about how far I want to go up on this graph if I want the scale to be relatively accurate, which some people don't care about, and that's okay. As long as you've labeled things clearly, you're going to be fine. Let me get that out of the way. Okay, so now let me switch back to purple. Let's go ahead and start graphing our points. 0, 0, we're at the origin. Pi over 2, we're way up here to 3. Pi 0 puts us right here. 3 pi over 2, -3 is right here. 2 pi 0. And the great thing about sine waves, everybody, they are completely symmetrical. Once you've kind of figured out the spacing, you can work forwards or backwards without doing a whole lot of work. At -pi over 2, we're going to be down here at -3. At -pi, we're going to be right back here on the x-axis at 0. At 3 pi over 2, we'll be up at -3. And at -2 pi, we'll be back at 0. So it just kind of follows this same zigzag pattern over and over and over again. Now, with a 3 out in front, forget what I said on the last problem about a 45-degree angle passing through the x-axis, because that's not getting us near this point, which we need to hit right there. So forget that, guys, but it should still be a curve here that comes through and is kind of bent downward, and it still should be horizontal as it passes through all of these peak points and valley points right here. But I've got to make the curve a little steeper than that as it gets through there. Okay, so that's one decent hump right there, and then we'll kind of just keep going. And all right, got to get back to the origin now, so that one's going to come up here. And if my spacing was right on my graph, hopefully this thing is going to be relatively symmetrical as it comes through all of these 9 points. And all right, guys, it's certainly not perfect, but I definitely think that that's good enough. So that's our graph of y equals 3 sine of x. Now, probably don't want to put this in your notes right here, but the parent graph we drew just a second ago only went to about here and here. So the parent graph, which I'll often draw is the green dotted line, looked something like this from the last problem. And what I hope you guys can see is that this graph that we're drawing here in purple shows that vertical stretch of a factor of 3. Let's go through some of those same things we talked about just a second ago, because you guys always need more practice at these ideas. Domain, the set of all x values, hasn't changed. This thing is still all real numbers. It goes from left to right with no gaps or jumps or anything in between. Range now, the set of all y values, now that's changed. Now we're going all the way up to 3 and all the way down to -3. So we would say -3 is less than or equal to y, which is less than or equal to +3. Okay, couple of other ideas right here. Amplitude, there you go. The way we measured amplitude was from a peak value right here back down to the center line. That is going to be 3. So that's what this number right here tells us, guys. That's going to be our amplitude. And then the last thing I wanted to discuss with you guys, the period of this graph. How long does it take to repeat itself? Well, we started here and it ended over here. The period is once again going to be 2 pi. Changing the period of a wave is something we're going to mess with later on in this chapter, but not really here in 13.4. So, hopefully, that one seemed a lot easier to you than the first one that we did. And this next one should just be a little variation on that. But I hope you guys are starting to get that once you get the hang of this, this really isn't all that bad. Okay, y is equal to a -1/4 sine of x. So what I can tell already, guys, is that this number out in front, which in the last problem was 3, that is your amplitude right there. So our amplitude on this problem is going to be, -1/4. Now what the 1/4 does is it's actually a vertical compression. This graph is going to be shorter, stockier than it normally would be. But I also want you guys to pay attention to the fact that this is a negative coefficient. And what the negative usually does is that it flips the graph over the x-axis. Okay, so let's keep that in mind. Now, even if you're not quite certain about all that, when you make your table, I think you're going to see what's happening. I'm going to do the same 5x values we've been doing here. 0, and then pi over 2, pi, 3 pi over 2, and then finally we'll end that at 2 pi, even though it certainly does go on further. And let's try to figure out what y is at each one of these spots. So I'm hoping you guys are knowing your sine values pretty well. If not, it's never a terrible idea just to sketch yourself a small unit circle and say, okay, where am I and what am I doing? At 0, that's this point right here. Sine is your y-coordinate, which is 0. So the sine of 0 is 0 times a -1/4, still 0. Here's where it gets interesting, though. Pi over 2, right up here. Sine is your y value there, which is 1. But -1/4 times 1 is a -1/4 at pi over 2. Okay. Pi, our third angle, right over here. Your y-coordinate is 0, so sine of pi is 0 times -1/4, 0. How about at 3 pi over 2, right here? Sine is your y-coordinate there, which is -1, and -1/4 times -1 is going to be a +1/4. 2 pi gets you right back where we started right there. Sine there is 0 times -1/4 is 0. So we got our table made. Let's take a look now and let's draw our graph here, everybody. So here's going to be your x-axis, and your y-axis can go in the middle roughly right here like this. Let's label with the space that we have here, guys. Again, I'll go to 2 pi right here. Halfway there is pi. We've got a pi over 2 and a 3 pi over 2, and I'm going to go this way. 1, 2, 3, and 4. There you go. That's -2 pi. That's -pi. Close enough. Now, here's the fun part. The y-axis right here is going to be kind of weird. Remember, guys, that this distance from here to here that I just drew in red is roughly 3. This distance from here to here is about 1.5. Okay, so when we drew the first graph right here, we said that our value of 1 on the y-axis should be a little bit less than that, so maybe that was 1. Now, though, our amplitude is just 1/4. So we need to go significantly less than that, everybody, maybe from about here to about here. So this is going to be a really short graph. I actually don't need that there at all. I can get rid of this red line. You go away. I didn't really need that there. Yeah, this is just a 1/4 right there, and then a negative 1/4 right there. This is going to be a pretty stubby little graph because it's a vertical compression. So let's plot our points, guys. I'll do this in purple again. Once again, we've got 0, 0. Then, now at pi over 2, we're actually going down this time instead of up. If you take a look, guys, in the last two graphs, the second point that we drew was a peak. It was a high point right here. But now it's a low point. It's a trough, and that's because of the negative that's out there in front. This thing flips over the x-axis. Pi gets us back to 0 right there. 3 pi over 2 is 1/4. 2 pi is 0. And again, I can kind of read this thing backwards now, guys. At negative pi over 2, we're going to be up here at 1/4. And then at negative pi back at 0. Negative 3 pi over 2 will be down to negative 1/4. And 2 pi will get us back to 0 there. So again, just kind of guessing as to what this thing is going to look like. I'm trying to draw a nice smooth curve that doesn't take any weird jagged turns. That's roughly what this graph is going to look like. So looking at this graph in comparison to the other two big changes, guys. We have the vertical compression right there. This graph is significantly shorter, less tall than the previous was, and this one flipped over the x-axis. The first two graphs we did went up into the first quadrant to begin after they left the origin. This one, on the other hand, goes down into the fourth quadrant, and that's because of the negative leading coefficient. Real quick, let's finish this one up, guys. Domain. Set of all x values is, again, all real numbers. And by the way, I hate to ruin the suspense. That'll be the domain for every sine function you ever graph. Range. This one is limited right now. The minimum value is negative 1/4. The maximum value is positive 1/4. So negative 1/4 is less than or equal to y, which is less than or equal to positive 1/4. Okay, amplitude, there you go. Technically, guys, amplitude is the absolute value of that negative number right there. So we would say that the amplitude is 1/4, not negative 1/4, but I don't think I would take off if you guys gave me that. And this one here, yet again, the period is how much space or time it takes to repeat itself of one full cycle. Like from this point to this point over here, yet again, the period is 2 pi. As I said, we'll change the period, I believe, in section 13.7, but not here in 13.4. All right, guys, that's all I wanted to do with you for this video here. That's kind of just a quick 3 quick examples right here to illustrate what a sine wave looks like, how you figure out what its graph looks like, and how you can draw that reasonably accurately doing it by hand. So hopefully you've got a sense for how that works. Let's dive into that homework and see how we do. Good luck, everybody.